Hi folks, welcome back to my house. Um, Today we're going to start the first of what I believe will probably be three installments on what are referred to as mixed models. And so to start off, I have some data that we can play with, and it is saved as an R object, very similar to how this week's homework was. So here I can load it in. So it's saying loads, split a yield, and now I have this object called yields that is now in my workspace. So let's first set up the general design of this experiment. And so we're interested in the effects of either being irrigated or not irrigated, the effect of being at low, medium, and high density, and then various fertilizer combinations, nitrogen, and phosphorus. And you can see here that we've done this across 4 different fields. People were nice enough to let us use their field to do these experiments. And the response variable of interest is the yield. And so what we want to know is whether or not any of these factors. And so let's start something with just a really simple thing, and let's just think about irrigation. So we could make a simple linear model where we are going to think about the effect of irrigation on yield. Okay, and this is the same kind of a linear model that we've been building now for three or 4 weeks. So we go ahead and we can do that, and there we have the parameter estimates from our linear model. This should obviously all look very familiar to everyone, and we can think about what we're actually doing when we do this. There's a box plot. Here is the control. Here is the irrigated. Again, we're interested in whether or not there's an effect of irrigation on the yield. And just by eyeballing that box plot, it looks like there probably is. And of course, as we've talked about a number of times behind the scene, what is happening is the computer is using dummy coding, and it's really looking something like this, where we have all of our data, where this would be 0 here for control, because alphabetically it becomes before irrigated, which starts with the letter I, in case that was unclear. And so here we have our control in the irrigated. And again, if we put that model, or if we put the line to the model, that's essentially what we have modeled. And that's where we're, and that's where we've been, right? We've been setting up linear models, and we've been thinking about it. But now we're going to think about something that maybe we haven't considered when thinking about our data. And so there is a certain level of non-independence that we have among the various fields, right? Because we've replicated this experiment 4 times in field A, field B, field C, and field D. And we might want to account for the fact that, first of all, that there is non-independence or relative non-independence among the different fields. That is, the random variables that we're grabbing for yield. We would expect that if you're in field A, you might be more similar to other things in field A as opposed to the samples that you're taking from field B, etc. And so this is where the concept of a mixed model comes in. And mixed models are often referred to as random effects models. And what we want to think about are what do we mean by a random effect? So a random effect is an effect that basically varies in a way that we don't have any control over, or that is explicitly not interesting to us in the context of hypothesis testing. And so here, field would represent a random effect, because we could imagine that those 4 fields that we have are 4 samples from a population of possible fields. It just so happens that we happen to have done it in those 4 fields. And so we would want to treat field as a random or varying effect, so that we could basically account for variation that might just inherently occur among fields. You could imagine, one field might have had soybeans last year, one field might have had corn last year, another field might have been, just kind of left fallow for a couple of years before we decided to come in and do our experiment. And another field could be an old brown field. It could be an old industrial site, but we happen to be doing the experiment there. So if we want to test hypotheses about, for example, the effect of irrigation, and later we'll do the effect of density and the effect of fertilizer, what we're going to want to do is we're going to want to account for that variation among fields. And there's really kind of two different ways that you can think about why that might be important. The first reason why that might be important is we do want to explicitly account for the non-independence of the data that we're taking from each of those different fields. That just seems like the honest thing that we're going to want to do when we're estimating our parameters. The other reason why we might want to do it is it might actually increase our ability to detect something. And that's because up to this point, we've just been dumping all of the stuff that we do not know into the common error term. So I'm going to use my fancy new whiteboard here and think about what we have done historically. So historically, we would be interested perhaps in yield being some function of what, being some function of irrigation. Let's just call that the model for right now, because that's just a generalized statement of what we've been doing up to this point. And then we've just had an error term. And when we were doing the hypothesis testing, what were we doing? We were looking at the ratio of the variance component that our model is explaining of our data versus the variance component that we're unable to explain given our data, which is why when we calculate that F statistic, right, we take the mean squared of the model divided by the mean squared of the error, and that's how we that's how we've been calculating our F ratio. So what we're going to do in a mixed model is we're going to appreciate the fact that we actually know a little something about this error term. It's no longer junk. It's the variation that we're unable to explain in our model, but it's not variation that we totally cannot explain. So in our case here with our model, make this maybe a little bit bigger because it is a whiteboard. There we have it. So what we're going to do when we set up a mixed model is we're going to put structure to this error term. And so you could imagine, given our example here where we're trying to predict yield, that instead of just saying plus error, we're going to have the error maybe among fields and then the leftover error. Leftover. How am I doing here, folks? Right. So now we've put some structure to our error term where we have the error among fields, which is what that spells, even though it looks like it said Phelps. We have the error portion that's among fields, and then we'll also have the error that's still the leftover residual thing, or residual term. And the way that you can think about how this might increase our statistical power to detect an effect is that if there is a lot of variation among fields, and if all we're doing is setting up a simple linear model, we're taking that point estimate across all fields, if there is quite a bit of variation among fields, we're going to have a lot of variance that is going to be unexplained because you're going to have a lot of points that are far away from that grand mean. If we can get rid of the among field component portion of the variation, now we'll have less error that we truly have not accounted for and that we can't explain. And we could imagine a scenario where then if we look at the ratio of really what we can't explain left over versus what we can explain in our model, that we're going to have increased power. And so this is what is referred to as a random effects model or a mixed model. Okay, and so let's go back and think about for a moment what we're doing here with our data. Oh, and I will mention that this type of a design where we've redone this experiment 4 different times, essentially across all of those fields, is what's often referred to as a blocked design. And so each block here, each field, is receiving all of the possible treatment combinations. Okay, and so if we think about it, let's go back and we're looking at our yields there, but I'm going to just go ahead and think about what we might be interested in doing. So here, get me out of there. Come on. Oh, there we have it. So here I've made a box plot where this is field A, control and irrigated. This is field B, control and irrigated. Field C, and field D. Okay. Again, the hypothesis that we're interested in at this point is whether or not there's a difference between control and irrigated. And we can see that overall it looks like within each of those fields, control is always less than irrigated. But note that there is some evidence, just by eyeballing this, that there is a difference among fields. So field A overall just appears to have lower yield compared to fields B, C, and D. And that's the portion of the variation that we are going to want to account for when we're setting it up as a mixed model. And so let me make that small again. By figure. By. Okay. Ooh, look at all those warnings. Okay. And so how we're going to set up a mixed model, and there are two primary packages that are in R that people use to set up mixed models. I'm going to use the one that everyone has kind of gone to. If you look at an earlier books or older books, I believe it was called ADE4, which was a model for doing random effects models, whereas we're going to use what's called LME4, which is what I would say 95% of people use now for mixed models. I just wanted to mention that the other package exists because some older tutorials online and some older books might have, they might be using the different package, and the syntax is different, and it seems like a waste of time for us to learn the syntax of two different libraries when everyone is using LME4. So we would say library LME4, going to load that in. And so the first thing I can do is I could try to make a model. So let's call it mod because I tend to like calling things mod. And now since we're going to do a mixed effects model, we're not going to use LM as the function. We're going to use LMER. Elmer is what often the kids refer to it as, Elmer. So we're going to set up an Elmer where again we're going to have a yield as being some function of irrigation, and then our data again will be yields. So what I've done right here is I have typed the identical model that we had up here with using the LM function as a linear model. Here I'm doing it as an Elmer. If I run that, I will get an error message, and the error is that there's no random effect specified in the formula. So we're going to have to tell it what we want the random effect to be based on. In our case, what we're going to do is we're going to put field in there, because we're going to assume that field is the random effect. And again, we can think about the reason why we're treating field as a random effect is because those 4 fields were sampled from a population of possible fields. And again, we can assume that there might be differences among fields, just inherent differences among fields, and we're going to want to account for that portion of the error. And so the first way, or the first thing that we can do is we can assume that the treatments might have an effect across fields. But let's assume that each field has its own intercept. And by its own intercept, what are we saying? Again, if we think about how dummy coding and stuff works, we're going to assume that each field has its own baseline for the effect of the control treatment. Because we know that alphabetically control is going to come again before irrigation. And what we're going to do then is we're going to think that each field has its own baseline. So that way when we generate a parameter to think about the effect of irrigation, we can think about it as all being kind of scaled or relative to a different intercept for each field. And so how we do this in the LME4 package is we tell it that we want each field to have its own intercept. And we do that by saying one pipe field. Okay. And so what this piece of syntax right here is telling us, or telling R, is that we would like to model this as a mixed effects model, and we would like each field to have its own intercept. And this is how we will account for that, or for that random effect. So I will go ahead and say mod. Now I don't get an error message because I have put this term in there, and we can go ahead and let's take a look at our mod. Okay, so here is our mod. Notice that now the output is slightly different than when we had just a straight up linear model when we looked at the summary. We still have the information that's included up here, which is what our formula was. And now we have these random effects portions. And the random effects portion, this is the variance of the error term here that is explained among fields. And then here is the variance that's left over. And so we've gone from a model where we've basically been able to cut in half the amount of variation that we cannot capture with our model. Let's compare that to our simple linear model, and we can see what some of the differences and what some of the similarities might be. Nice. Okay, so that's our linear model, and then that is our mixed model. And so here's our straight up linear model, right? No random effects in this model. And notice that we have, again, our intercept, and then we have the effect of being irrigated. So on average, you would expect if you're irrigated, the yield is going to be 21.4 greater than if you were not irrigated. And if you were not irrigated, that's the expected amount, right? We already understand how we can interpret those parameters. If we go down to our mixed model, note that the parameter estimates are the same. So the magnitude of the difference is the same. The model is still capturing that. What has changed, however, though, is the uncertainty around those parameter estimates. So here, notice that we have a standard error of 3.4 around the intercept, whereas when we set it up as a mixed model, we have a standard error of 8.598. So why might that be? When we did it as a simple linear model and we weren't accounting for the among field component, we had a lot more information for that parameter estimate, right? Because we assumed that they were all random variables drawn from the same thing. As you increase your sample size, you're going to decrease the standard deviation. All the standard error is the standard deviation around your estimate of the mean, which is the intercept. And so by setting it up as a random effects model or as a mixed model, we've actually increased slightly the uncertainty around our parameter estimate for the intercept. However, in this case, if we look at what's happening to the uncertainty around our estimate for the slope, in our standard linear model, the standard error is 4.926, and in the mixed model, it's 3.56. So we've actually decreased the uncertainty around our slope estimate. And why might that be? Well, the reason why that might be is that there was an inherent difference among the different fields. And that means that we had a lot more spread around all of those, around that slope when we put a single slope there. By removing the variation among fields, we've actually decreased the uncertainty around our slope estimate. And in principle, then, we might have, as a consequence, increased our statistical power to detect an effect. One other thing I want to mention here is this part right up here where it says it's a linear mixed model fit by REML, R-E-M-L. And what REML is, where is my, oh no, already lost it? God, Jim, what are you doing? Okay. REML stands for a number of different things, but they all have the same acronym and they all essentially mean the same thing. The ML part stands for maximum likelihood. So that's good. Maximum likelihood. Okay? The R part of that can stand for one of two things. It can either stand for residual or restricted. Either of those are totally fine terms that we might decide we want to use to describe what REML is. So what is it? That's a good question to start with. What it refers to is that when partitioning the error structure, when we're setting up a model, a mixed model, it is using maximum likelihood to estimate the parameters associated with the error term, but then once it establishes the error term using maximum likelihood, then the rest of the model is done just as we've been doing linear models since we began, which is ordinary least squares. And so we're only restricting maximum likelihood to the error component of our model. And so why might we do that? We know that maximum likelihood estimates are always going to be biased. And they're going to be biased because the observed data is always going to be closer to the parameter estimates based upon the observed data than the true population data. So for example, the maximum likelihood estimate for the standard deviation, those are always going, all of those data points that are used to calculate the variance are going to be closer to our estimate of the mean than the true population mean. And if you remember way back early on, that's one of the reasons why we have that n-1 in the denominator when we calculate the variance. It's to get rid of that particular bias. And so what REML then is doing is it's using maximum likelihood for the error term, and then the rest of the model is being done kind of as a standard as a standard ordinary least squares. There is an argument within the Elmer function that you could actually say REML equals false, I believe. Let's see here, question mark, Elmer. Let's take a look-see here. Right here, there is an argument, REML equals, if you had said REML equals false, then it would fit the entire model using maximum likelihood. And again, we'd rather not do that because even though maximum likelihood sounds a little bit more fancy, we know that it would be biased, and we'd like to have the best unbiased estimator that we could possibly have. Okay. And so we could even look here. Let's go back to where we can look at things and see what REML did, right? So here's our REML. Here's our random effects again. Here's our fixed effects. And if I were to use this function called coef, which will give me the coefficients, here we can see here are the different intercepts, because again what we did is we allowed each field to have its own intercept, so its own baseline. And these are the means within the group. So here again, here's that field A, which always looked like it was underperforming compared to the other three fields. And here are, here's field B, field C, field D, etc. And so this is what it was being estimated using the maximum likelihood portion of it. These are our different intercepts. That's the part of the error term that we are putting structure to. So it's not that we don't know what's causing some of that variation. We just don't necessarily care in the context of hypothesis testing. So we want to account for it, but we're not necessarily doing hypothesis testing on it. And as a consequence, that's why we're using the general linear mixed modeling approach. Okay, so one other thing that I will mention is that there could be a scenario where you would not treat field as a random effect. So don't always assume that fields or growth chambers or whatever they might be, anything that you would block by, don't always assume that they have to necessarily be random effects. So one scenario here where you would want to treat field as a fixed effect is, imagine you were hired as a consultant by somebody who was going to buy a field, and they were going to buy one of these 4 fields, and they wanted you to do the experiment to find maybe the best field, the one that has the greatest yield, et cetera, et cetera. In that case, you would want to include field as a fixed effect because you would actually be interested in variation among the fields. Whereas in the scenario that we're doing right now, we are assuming that the field is just not nuisance, but just a random effect that we don't really have that much control over. Okay, so that ends this little part. What we've done is we've set up a very simple mixed model. We understand why we did that and what what we're doing by allowing each field to have its own intercept. So what we'll do next time is start thinking about hypothesis testing, because I don't know if you noticed, but there is no p-value here when we did summary, right? We got a t-value, no p-value, whereas with our standard linear model, we get a t-value and a p-value. So what we'll do next time is we'll talk a little bit about the hypothesis testing part of a mixed model. So go team. Talk to you all soon.